Okay. So everyone can hear me and also see the PowerPoint?
Looks good.
Great.
Sounds good.
Yeah. Thank you very much, Ben and Joe, for organizing that. And thank you, everyone, for coming. So this is my PhD colloquium talk I have given a month ago. It may be a little bit longer than half an hour, but I will try my best to make it short. And the topic today I'm going to talk about is modeling deformation and the seismicity during volcanic unrest. So I cannot finish this work without the help of my advisor, Trish Grigg, and all these wonderful collaborators. So after the motivation part, my talk will be divided into 3 parts, and I will show you how these first two part, data simulation and uncertainty in the model, can serve as tools for me to understand the volcanic unrest. And after that, I will give you the conclusions and some future directions. So first, why forecast the volcanic? I want to understand the volcanic unrest? Because one of the grandest challenge for volcanologists is to forecast the onset of volcanic eruption. So it's very hard, but luckily for most of volcano, before it from this happy phase to eruption, it will experience a period called unrest. So due to the possible magma migration, storage evolution, the physical conditions surrounding the magma reservoir will change dramatically, which will make the surface to deform or create some failure, which is earthquake, and also degassing. So in my talk, I will focusing on ground deformation and earthquake. So what can deformation tell us? So here is a study by Julia Biggs from global data show us the relationship between the deformation and eruptions. We can see for those volcanoes without any deformation, only few them erupt. That is good. So that means for most of volcano, we do have something for us to do forecast. However, not all deformed volcano end up with eruption. So that means it's not easy, just use displacement to do forecast. So on the other side, what can seismicity tell us? Here is a study by Diana Roman, and here is the depths of the volcanic tectonic earthquake evolution before the eruption. We can see different volcanoes along the evolution arc. For example, the Okmak volcano, before eruption, there are almost no precursory earthquake. However, for Augustine, the precursory earthquake almost start a year before the eruption. And also for volcano with precursory deformation earthquakes, the depth distribution is also different. So different volcano has very different behavior. We cannot just using a simple pattern recognition to do the forecast. So what we can do? So we need to understand the physical process during the volcanic unrest. What we need is both high quality data and also quantitative model, which based on those physics. So for the data, we are very lucky since the data tsunami is coming, we can constrain the ground deformation by high spatial resolution INSAT data or high temporal resolution GNSS data. And also on the other side, more and more broadband seismometer has been installed on volcanoes, so we can know some information about the material failure process. On the other side, we have more advanced model. So more than half century ago, people already developed those analytical model with simple geometry and rheology, showing us the surface deformation due to a pressurized void. And with the development of modeling techniques, we can model volcano with more complicated geometry, rheology, and even model this void with some magma. For study the material failure process, so we can calculate the stress with some failure criteria to indicating the failure process. So the key question of my PhD work is to understand how we can take advantage of both data and a model to study volcanic unrest. So what I have done is first to create a data simulation work, which allow me not only to use data to constrain the model, but also the model can optimize the data collection strategy. Then I will show you some study in the model uncertainty, especially the rheological uncertainty when we model the fading of the magma reservoir. And third, I will show you some application of this workflow from two examples. One is Lagoon Damoli in Chile, and the other is Edka volcano in Alaska. So first, let's go to the data simulation. The data simulation strategy we are using is called ENKF, which has been widely used in climate and weather forecast. So how it works. So here is a simple volcano model, and with an inflating pressure source, the surface can create a deformation, which has been detected by the satellite. So we want to know what is this pressure source looks like. So instead of building one model, we build tons of models. They act like an ensemble and compare that with the data to get an updated model. So this updated model is depending on the data and the model, and also considering the uncertainty in the data and the model as well. So use that, we can get an updated model space. So basically this space will have a better estimation than our initial guess. So when we have more data at times equals 2, we can do this again, and again. So basically, if we have enough data, we can get a pretty good estimation of the pressure source by the surface deformation. So there's a few applications using the ENCAP to model the volcanic deformation by using the synthetic data or real world data. Although there's not many study, but those pioneer work has already showed that ENCAP is a robust and a powerful tool to determine the pressure source. And we don't need a very good initial guess, since the ENCAP can help us with the model and the data to determine those parameters. And Trish and I is already working on giving a tutorial on the GitHub. This is based on a tutorial we have given on the CIDR last year, and we have already published on the GitHub, and we want to publish another paper on that. So it is showing you some very simple way you can follow to do the data simulation if you are interested in. Okay, so let's move to the second part, the rheological uncertainty in model fading. So first, why I want to understand the effect of the rheological uncertainty. Since in a natural system, the rheology of the crust is usually poorly constrained. Only few volcanoes on the world has been well constrained by multiple geophysical observations. So we usually use some assumed value for the material property when we do the forecast of the fading. However, I want to understand if we already know the pressure source pretty well, since we can determine that by some data simulation strategy, but we don't have a good constraint on assumption. My question is, can we still do an accurate forecast of the fading process? So before going to that, I will give a brief introduction of how we calculate the stress and the fading if you are not very familiar with that. So the stress can be defined as a force divided by area. And in a material, if you give a plane, you can always find a normal stress, which is perpendicular to that plane, and a shear stress, which is parallel to that plane. So in a material, the stress state is tensor is very complicated. So when you give a different plane, those values will also change. However, if you plot the normal stress and the shear stress on the XY plane, you will get all those values are fall on a circle, which we call Moore circle. It's very good, since we can use a very simple circle to describe the complicated stress state of a material. To study the fading, scientists do the experiment to test when the fading happened, what is the stress state in that rock. We can draw a Moore circle on that. And by doing this test and a different stress condition, we can get another Moore circle. And for one material, all those Moore circle at fading are all tangent to some lines, which we call as fading envelope. It's a very good feature, since If we know the fading envelope, we can use that to predict fading. Whether or not the Mohr circle is large enough to touch the fading envelope, it's failed. And when it's far away from the envelope, it's not failed, it's safe. So here, let's go to a volcano model. Here's a very simple Mogi-like model. The overpressure creates a surface deformation, and this is normal stress and the shear stress. And I'm going to show you the stress state and the fade-in at different points. So this is the top of the magma reservoir. We can see the center of the Mohr circle is depending on the average normal stress, which is the center of the Mohr circle, which is depending on the pressure, the static pressure here. And the radius of the Mohr circle is determined by the maximum shear stress, which is controlled by the overpressure. So for here, this point, when we have in the overpressure is large enough, we can have a large Mohr circle touch the envelope to create fading. So at the same condition, when at the bottom of the magma reservoir, it has the same shear stress, so it has the same radius. However, the center of the Mohr circle is far away from the envelope. Since it's deeper, has a higher normal stress. Similarly, to this point, at the same depths, we have the same pressure with the same center of the Mohr circle. However, it has lower maximum shear stress, so the Mohr circle is smaller. It's also safe. So now I want to study how the fading development can be affected by the nature of the crust. So here is a elliptical magma reservoir. Since it's elliptical, the maximum shear stress is localized in this point. So that means when the fading happens, this point will be always the first point for the magma reservoir to fail. We can see for the weak crust, which Young's modulus is pretty low, when we have larger and larger overpressure, the magma reservoir start to fail at this point and create a surface displacement, for example, 2 meters. So at the same condition, if the crust is strong, it already failed. You can see here, there is some fade-in. It's already failed at only ½ meter of surface displacement has been created, even if the overpressure is the same. That means for stronger crust, lower displacement will be expected when fade-in initiated around the magma reservoir. So we can define this displacement when the first fade-in happened. It's a very important feature, since if we assume we are going to model a volcano with a weak crust, however, we don't know that. We think it's strong, so we use a strong model to do that. Okay, we observe a ½ meter surface displacement. Based on the model, it's already failed. However, it's far away from safe since it's a weak. So that's a false alarm. So that means if we don't know the Young's modulus of this model, we may get a very inaccurate forecast of fading. So to detailed study the relationship between the weakness and this critical displacement at fading, we plotted the Young's modulus, which described how strong rock it is, and against this critical displacement at fading initiation. We can find that for Young's modulus, which is low, a little change of the Young's modulus will create a huge difference of our predicted critical displacement. However, for Young's modulus, which is high, the result is not sensitive to Young's modulus anymore. Also, we explore another elastic modulus, which is Poisson's ratio. The Poisson's ratio describes how difference between the lateral and axial deformation. So we can see for model with different Poisson's ratio, they all class together with the model with same Young's modulus. That means the Young's modulus has a much greater effect than Poisson's ratio when we do the forecast. So to summarize, the second part showing us the fading onset is more sensitive to Young's modulus than other material property like Poisson's ratio. And the material uncertainty for a stronger rock or stiffer rock, which Young's modulus is larger enough, has little effect on the fading forecast. However, knowing the Young's modulus for the crust is very important, especially for those shallow systems, since usually the Young's modulus is pretty low for those shallow systems. And now let's go into the third part, the application of volcanic unrest. Let's travel to Laguna de Mole. Laguna de Mole is a large rhyolitic volcanic system in South Andes, Chile. Here is formed at least 1.5 million years ago. It has also still have numerous eruptions during the past 20,000 years. So since 2007, this volcano experienced a very rapid surface uplift, like 20 centimeters per year. So it will create displacement in 15 years as high as the roof of my room. And at that time, everyone is asking whether or not this system is going to erupt or not. So besides the geodetic data, we also can have some study on the earthquake. So this is a study from Cardona showing us some earthquake swarm during the unrest. We also have the seismic tomography, gravity, and magnetotelluric data give us some hint of this magma reservoir with the weak, low density, maybe high conductive body there. And besides, we also have a microgravity change during this period of time, indicating there might be some mass migration during the unrest. So the Laguna de Mole is an ideal place to study the volcanic unrest since we have multiple observations. So my goal of this study is to explain all those data. What I'm going to do is first, we are going to use the data assimilation strategy I have described in the first part by the INSAR and the GPS data to determine the pressure source. And then this pressure source can compare to the other geophysical observations. And with that, with the pressure source, we are going to calculate the stress we have introduced in second part to see if we can explain earthquake, gravity change, and some other observations. So finally, with those observations, I want to understand whether or not this system is going to erupt or not. So first, this is the model we use to model surface deformation. We model the surface deformation in Laguna de Mole by this ellipsoid pressurized void. It can tutor in three dimension in the space. Since we already know the rheological structure is important, so we use the seismic velocity profile in this region to constrain the rheological structure. And also we considering the temperature effect in this volcano. So you can see here is the Young's modulus profile. In the far field, it's determined by the seismology, and when it's close to the magma reservoir, it's also affected by the temperature. Whereas a higher temperature, it has a lower Young's modulus since it's weaker. So now we are going to use the data simulation with the geodetic data to determine the pressure source by our model. So we are using the multiple INSAR tracks. Since they are all come from different looking angle, it can give us a better constraint on the geometry. So our model shows it's pretty consistent with the observation by the INSAR. And by the ENKF, it can provide us the parameter of this pressurized ellipsoid, which is XYZ is the location, R1, R2 is the size, and the tutoring angle by the direction and the deeping. So the ENKF gives us a distribution of the parameter. We can use the mean value of those parameters as a best fit model and compare that with other observation. So here, I'm going to show the green one is the pressure source we determined by the geodetic data, and the red one is the tomography data with the low S-wave velocity body, and the blue one is the low density body by gravity. We can see in generally they has the same location, and also the tutoring trend is the same. However, the size is different, and also even tomography is not consistent with the gravity data. So besides there may be some uncertainty in those observations, we think the possible explanation will be we are imaging crystal mush here. It's highly heterogeneous, and also different part may have different fraction of crystal, liquid, and bubbles. So different geophysical observation is different from is sensitive to different physical properties. So we may imagine the different part with different physical property. So now, in general, we use the geodetic data to constrain the pressurized source, and this can comparable at least to the tomography and gravity data. Now let's see if it can explain earthquakes. So to calculate the to indicate the earthquake, we are using the stress calculation and failure envelope to see if we can create some failure that we can indicate the earthquake process. So by geodetic data, we know at the end of 2016, the overpressure of this pressure source is about 6 megapascal. And by calculating those failure envelope, we found there's no failure at all. We cannot create any failure to explain those earthquakes. If we want to have some failure, we need an unreasonable extrapolation of the overpressure to about 50 megapascal. And it will create about a 20 meters surface uplift, which we don't observe. And also, even if it has some failure, the pattern of the failure, the region of the failure is not consistent with the distribution of the earthquake. So that means this model doesn't work. So how we explain the earthquake? Let's go back to the earthquake distribution. We find those earthquakes all seems to be controlled by a fault. Since in our original model, we didn't model that fault. Now we add a fault, which the fault is a weak zone whose Young's modulus is low. And now let's explore the effect of fault. Here is the result of unreasonable high overpressure without fault. And when we add a fault, oh bummer, there's even less failure created. Since it's easy to understand, fault is a weak zone, so it's easy to deform. So under same surface deformation, it creates less stress, so it has less fault. So how can we create failure, since we want some failure to explain the seismicity, right? So one thing we can create failure is to enlarge those Mohr circle to make it touch the envelope. But also we can use another strategy is decrease the normal stress, which move this Mohr circle towards the envelope to trigger failure. And it can be done either by increase the pore pressure or unloading. Since there is no strong weathering or deglaciation in this region, we think unloading is less possible. So we're considering the effect of pore pressure. So here is a cross-section of this pre-existing fault, which is Tankershell fault here. And this is the magma reservoir, this is the fault. Since it's a pre-existing weak zone, so we expect to see there may be some micro fractures in the fault zone. So with the inflation of this magma reservoir, some part of the fault will experience a dilatancy, where the volume will increase. We argue that this increase of volume may either achieved by the growth of some microfractures or can connect some pre-existing fractures, which in the end will increase the connectivity of the pre-existing fracture zone. So when the permeability of the fault is increased, it allows some fluid to go into this part. And when the overpressure is increased, it can trigger earthquakes. So far, it can somehow explain the earthquake. So we want more evidence to see if that process is correct. So as we know, when the fluid inject into those pre-existing faults, so some unoccupied microfractures may now be occupied by some fluid. That may increase the density of the rock. And we calculate the density increment due to the fluid injection, and we can calculate the surface gravity change due to the density change here. And we can see the model of the gravity change can somehow consistent with this gravity survey by Miller and al. So far, so good. And also, one thing to notice that is, if we have a fluid going shallower, those fluid can decrease the electrical resistivity of the rock, which will create a weak conductor by the MT data. So far, we explained all these geophysical observations. The last question I want to answer is whether or not the unrest will lead to eruption or not. So we can see here in Lagrange-Damali, the inflating magma reservoir makes some part of the fault have a volume increase, which increased connectivity, allow fluid going to it, and move the Moore circle to trigger the earthquake. And the fluid can keep moving upward to create some positive gravity change and also some low resistivity zone. So we argue that the pore pressure increasing will trigger the earthquake, actually release some stress accumulated in the fault zone. So it will, at least will make this part more stable. Okay, so now let's go to another system, Etka Volcanic Center. So Etka Volcanic Center is at Central Aleutian. There's also some pre-existing fault there. And during 2006, from the inside data, we see there's an acceleration of surface uplift at the center of the Etka volcano. At the same time, we also observed there's an increasing number of seismicity. It seems all controlled along this AA fault. And at the end of 2006, there is a phreatic eruption happen at one of the volcanic vent in this volcanic center, which is Carving volcano. And a few weeks before the eruption, the crater lake of Carving disappeared. So the question for this system is whether the volcanic unrest happened in the center of this island can relate it to the phreatic eruption happen in the Carving, which is 5 kilometers away from the center. So very similar to the Lagrange-Damali application, we use the INSAR data to constrain the pressure source. So here is a movie. I can show you here. You can see with the INSAR data come in, actually the pressure source is evolving to fit those INSAR data. And here is a 3D view. If you can see from here, it's open box for a 3D block. And also this showing the current time during the evolution. We can see before the eruption, the earthquake swarm is increasing. So now it's the eruption. So okay, as similar as the Lagrange-Damali study, we also want to see if this over-pressurized source can create some failure to explain the earthquake. And very similar, at current overpressure state, there's no failure at all. We need at least 3 times more overpressure to initiate failure. Since we already know those earthquake is not just triggered by the overpressurized source and why there's earthquake. We have the experience in Lagrange-Damali. It is showing us some pre-existing fault zone may dilate due to the evolution of the pressure source, then create a larger permeability, let the fluid go into it to trigger earthquake. We want to explore if this process is also the case in Etka volcano. So we see the earthquake is distributed along this AA fault. So we model this fault, and to calculate the volumetric change, the volumetric strain of the fault due to the overpressure. So we can see the red part, which show us the volume of the fault is increased. And you can see this red area is consistent with the distribution of the earthquake. That's a good sign, since we know the volume increase of the fault may trigger earthquake. And further, we can calculate the evolution of this volume change due to the migration of the pressure source and compare that with earthquake. we find that the earthquake is favored those red area, which the part of the fault experience dilatancy. So there is some spatial correlation. So what about the temporal evolution? So we can calculate the energy released by the seismicity along the fault. We calculate that along the fault within 2 kilometers up on the box here. And then we can also calculate the total volume change by integrating the volumetric stream. And we can see the total volume change and energy, they all share a similar pattern when it's normalized to its maximum value. That may tell us the energy somehow is proportional to the volume change of the fault. So why? So a preliminary explanation by the mechanics of microfracture is showing that in the micro scale, which we have a millimeter scale fracture, we can calculate the energy released by the opening of this microfracture. So the microfracture, we assume it has a simple shape of an elliptical cylinder with a volume V. So the energy release, it can be expressed by here, T is the tensile tensile stress of the material, and E is the Young's modulus. This term is the aspect ratio of this ellipse, and also the V is the volume of this microfracture. If we assume the material has a constant property T, constant property here, and also it follows a self-similar propagation ratios. That means the aspect ratio of this crack is keep constant. Then we can get the energy released by the opening of this crack is proportional to the volume of the crack. So this is a very preliminary explanation. We didn't consider many other aspects, but it gives you some hint that the spatial and the temporal relationship between the earthquake and the fault dilatancy may indicate that the hydrofracturing processing is the key to explain some part of the volcanic tectonic seismicity for some volcanoes. So that means water is important, right? So finally, I want to ask why the volcanic unrest can follow up with a phreatic eruption. So we already know due to the dilatancy, the fluid may inject into the weak zone and to trigger earthquake. At the same time, the water table in the island may be dropped due to the water migration into the sink. And then when the water table drop, the crater lake incurving may drain and trigger the phreatic eruption. So for the conclusion, the first part data simulation, we show that ENCAV is a robust and powerful tool for doing the data model comparison to model the volcanic deformation. We don't need a good guess at the very beginning. And the second part, we show the Young's modulus is a very important rheological property for model. Since for some volcano which has low Young's modulus, we cannot get an accurate forecast without no Young's modulus. However, for a stronger crust, the Young's modulus is not a big issue. We can do a pretty good forecast without knowing the Young's modulus. And the last, the volcanic unrest in Laguna de Mole and Attica, showing us the water or fluid is somehow the key. Since in Laguna de Mole, the water triggered earthquake and release some stress, make the system stable. But for Attica, the water table drop directly triggered the phreatic eruption. And also we know the multiple observation is critical for us to understand the volcanic unrest. Here are some future directions I want to do when I get to Carnegie. First is to consider the effect of the accumulated damage when we studied the surface deformation and earthquake. Since so far, the model can only accurately forecast the onset of the fade-in at the magma reservoir. Once the fade-in has been created, the material property is already changed, so we didn't consider that effect. So in the future, I want to consider that effect. And also Another direction, which is more ambitious, is to study the magma reservoir dynamics from the crystal mush perspective. Since so far our model is a very simple model, it's very like a balloon. It's homogeneous since we use void, melt, or some porous media to study inside this balloon. It's controlled by a uniform constitutive law. However, in the reality, the magma reservoir is a crystal mush. It's very complicated. It's heterogeneous. It's like a mushy soup. So in different places, it has different fraction of crystal, liquid, and the gas. There may be no uniform constitutive law to describe the behavior of this crystal mush. So I want to study the dynamics of this mushy soup. It's very complicated, so I'm not expect I can finish that during my postdoc. So, but I want at least we start to do this in the future. Also, that's it. Thank you everyone for watching. Here's the question.
Thanks, Zhan. So right now, what we're going to try to do is Eric, myself, and Ben will try to moderate. If you could just use the raise your hand function, we'll try to call out. Zhan, you can either leave your slides up or we can move it to your face as you like.
Sure.
I should also note that one thing we'll also be doing is running a Slack channel. It already exists actually, and we'll use that to disseminate information about videos, as well as answer any questions perhaps offline that we don't get to today. So we have about 15 minutes or so for some questions now. Looks like Leaf has a question.
Please.
Oh, are you not? Okay,
oh,
there goes.
I think I cannot see raise hand here.
Oh,
so
yeah.
If you can, sure. Thank you.
Yeah. First of all, great piece of work. I really enjoyed that.
Thank you.
I guess I was wondering, well, lots of questions, but how you can assess the role of initial conditions in this type of forecasting framework, in particular, sort of stress and temperature, inhomogeneities, and perhaps anisotropy.
Yes, that's a very good question. Since for the static condition, for example, the heterogeneity, we may detect it by the tomography or other geophysical observation. That's the easy part since we can know. But for the stress, since we cannot measure stress before that, it's very hard for us to know the initial stress condition since there may be some residual stress from the last cycle of the eruption. So that's why I want to understand the accumulated damage, since the damage not only including the progressive accumulation of damage, but also including the recovery of those damage. So how, when after eruption happen, what is those fractures or the microfractures can heal, and what's that the evolution of the material process for the next cycle of eruption? It's a very important question. So for now, we Laguna de Moly, since we know that before 2007 there is been quiet for a very long time, so we assume there's no initial stress being accumulated due to the pressurized void. But for some frequent erupted system, there may be some residual stress. So that's those volcanoes we need to pay more attention on. Did that answer your question?
Sure.
Yeah, thank you.
All right, other questions? Kathleen.
Hi, nice job, Zhan. So in both of these cases, you mention changes in pore pressure, which is something that first thing that comes to mind is seismic noise studies, because the change in structure of a volcano is, a change in pore pressure, and being able to see that in seismic noise, changes in velocity and structure. For either of these volcanoes, are there data sets for that you could compare with your results?
Yeah, that's a very good suggestion. I haven't considered that, but I'm sure in the future I will pay attention to those data. Yeah, thank you very much.
Ben.
Thanks for a very nice talk. My question was, in the first part of the presentation where you show the data assimilation and a way of going from the poor guess and then converging on a more, hopefully more precise picture of what's going on, how long does that take to run computationally? Is this something that can be done in an operational setting?
So the computational time is depending on how complicated the model it is. Since we are using a Monte Carlo data simulation, that means we need, at the same time, we need around 100 models. If there's 100 MOGI model, we can do that simultaneously without any waiting. However, it's a very complicated 3D finite element model with reality is very complicated. It will take some time. So for the Laguna de Mole, I believe it take me like 3 days for using a cluster to get the pretty converged result.
Very good.
But for some, yeah, but for some synthetic tests, it's just run simultaneously.
Okay, now I think now Diana can ask a question.
Great job, Yan. I just wanted to ask about the final modeling. So both of your examples, Laguna del Mole and Corrigan, you dealt with known faults. And I guess I'm just wondering, because we see these kind of off volcano clusters of seismicity in many places, and it's an open question what causes them. If you think it would be possible to actually run a similar type of modeling exercise in more of an inverse mode, I guess for lack of a better term, to assess whether a fault might be present in a place and what its orientation might be, to try and find unknown faults that might actually be influencing off-axis clusters in response to some deformation source that's removed from the cluster?
Yeah, that's a very good question. That's actually what we have done in our paper. I haven't got slides here, but I can tell you, since a very important thing we want to know, we want to constrain those faults is for the INSAR data, we can see there's almost no offset of those line of sight. So for building this truncosome fault model, we test different fault geometry and different fault reality, especially the thickness of the fault and how weak that fault it is. We actually get the result that if we have a very weak and wide fault, it will create a huge offset of those line of sight fringes. So that means, although for here, we cannot uniquely determine where the fault it is, but we at least can rule out some possibility that the fault cannot be that shape or that weak. So in the future, I think if a volcano with the surface deformation without showing any sign of a fault motion, it's very hard to uniquely understand the fault's nature. But if the fault is moving, it creates some surface deformation, we can do that. So for Laguna de Mole, since we already see there's no fault signal in the line of sight, so originally we didn't model the fault. However, we just test the fault in the later part.
Thank you.
Thank you.
Any other questions? Well, Jan, that was a really great talk, and I'm sure there'll be a lot of questions that come up in the Slack channel. And I would encourage everybody to log into that if you haven't already. And certainly the representatives from your universities can get you in contact with that information too. What will happen on that Slack channel and also an email is an update on the schedule as we develop it. And certainly there are lots of open slots. So if some of the people want to join on that, they can certainly do that and let us know. Are there any other points of discussion before we head off? Well, thanks everybody. This seemed to work pretty well. You know, we're getting used to the technology here, and but I think we're doing a reasonably good job. And again, it's great to see everybody and having these discussions, and looking forward to the next couple months of this, hopefully.
Yep. Thank you very much.
Yeah, thanks for organizing this, Joe, and everyone who was involved.